Welcome, this is lecture number 43. In this lecture, we are going to talk about geometric perspective of eigenvalues and eigenvector in linear time invariant system, as well as we will see in switch mode power converter. So, in this lecture, we are going to first recapitulate the vector field of linear time invariant system. Then we want to introduce the concept of eigenvalue and eigenvector with their geometric interpretation. Then geometric interpretation of switch mode power converter, how does the phase plane trajectory look like? And this will be the stepping stone or the concept build up that will build up the concept here, because in the subsequent lecture we will talk about geometric control or the boundary control or sliding mode control, where we need to visualize the vector field, and that is why the previous lecture as well as this lecture, these are very important. Then we need to see some MATLAB demonstration of vector field. First we will start with our last class where we left. So, where we deal with two systems, system 1 and system 2. In system 1 it was a decoupled system with the A1 A2 matrix that we have discussed. So, that means for this system, what was A decoupled matrix that we have chosen? It was like A1 0 0 A2, where we have chosen A1 to be minus 2, A2 to be minus 3. And A coupled matrix we have obtained by means of a transformation, and this is the A coupled. And what is the transformation? This transformation, that matrix is basically a combination of two vectors, which was Vx1 and Vy1 in our earlier lecture, and that constitute the transformation matrix. And this transformation matrix will soon find that this will be the eigenvectors of this particular system matrix. Okay, so, it is a unique in that sense, and it has a special property. How do you find eigenvalues and eigenvector, and what is the physical interpretation? So, first the property of eigenvector, that means we start with x dot equal to x. Suppose we start with not orthogonal form, any arbitrary form, but two vector Vx and Vy, okay, where x0 is the initial condition and the initial condition for this state. That means, when you write a dynamical system, it has an initial value problem. That means, we need to specify x of t at t equal to 0, it is x0, that we are taking about x0. Okay. So, that is what, if you want to solve it, we know earlier, if A matrix, even if it is not in diagonal form, we can find out A1 and A2, and we are going to see what are these A1, A2, and we can write it in this form, and this is the initial condition. Now, we know how to write initial condition. If you substitute t equal to 0 here, t equal to 0 here, this will be 1 and this will be 1. So, alpha 1 Vx plus alpha 2 Vy will be x0. Now, again we are starting this system. What we are considering, suppose we are taking the initial condition along Vx, for example. You can also take initial condition along Vy, no problem. So, that means I am just explaining by taking one basis vector, you can think of the other basis vector. So, if you take initial condition on Vx, naturally alpha 2 will be 0, because we are not taking any component along Vy. So, it is along Vx only, and since Vx and Vy are linearly independent, if you take along this axis, then the other axis component will be 0. So, that means x of t if we write alpha 2 is equal to 0, alpha 2 is equal to 0. So, it will be simply e to the power a1 alpha 1 Vx, and we know this quantity from here. So, it will be nothing but x0, correct. So, that means we are taking the component x0 in this case along this axis. So, suppose this is my x0 along this axis. Now, we have considered that x0 is along Vx, that means we have considered the x0 is along Vx. So, we are taking somewhere here, is my x0, it is along this line, okay, and the system dynamical equation is x dot equal to x. Then, if you differentiate x dot, you will get a into xt, because it is already the equation of motion, and in this case x dot is nothing but a1x, because we are taking on the axis, and you see if you differentiate, what we will get? A1 into, that means xt we know. What is our xt? What was our x of t? We have seen in the previous, x of t is nothing but e to the power 18 into x0. That means x of t equal to e to the power a1 t into x0. If we differentiate with this, and we know that this quantity is nothing but our x of t, which is coming from here. So that means we are getting x dot equal to x dot t is equal to axt and small a1 into x. Now what is ax? Again, x of t is nothing but this, and this is coming from here, right? Again, what is my x0? x0 is nothing but alpha vx, because this is coming from here. This is coming from here. Now we can rearrange, since e to the power a1 t and alpha, they are scalar, so we are taking out and we are forming a into vx. Okay. What about a1 xt? Again we substitute xt, because we have done xt and ultimately it turns out to be this. We do the same thing, and what we will obtain? First, for x we got e to the power a1 t alpha 1 into a into vx, and a1 xt is equal to this term, right. So this is alpha 1, these are alpha 1, because these notations has to be clearly, this is alpha 1, right, alpha 1. So now since we are taking along vx axis, we are not starting at origin, so alpha 1 is not equal to 0. E to the power a1 t, since we are talking about finite time, it is also not equal to 0. So that means if we take here, that means what is our a of xt, a of, what is our, if I write it down, what is our a of xt? This is nothing but e to the power. So what is our a of xt? A of xt, it is nothing but e to the power a1 t alpha 1 into a vx. And what is our a1 xt? This is again e to the power a1 t alpha 1 a1 vx. Okay. So from these two equations, so we are getting e to the power a1 t alpha 1 a vx is equal to e to the power a1 t alpha 1 a1 vx. Since this term is not, it is not equal to 0, so we will get this term. Okay. And if we, that means we can rearrange this to get this, and this is exactly what we generally write to get the eigenvalues and eigenvector. Since Vx is not a null vector, it is not a null vector, then this null space of this matrix, the determinant must be 0, and this is exactly the equation is derived to find the eigenvalues. And a into Vx equal to a1 into Vx, this to find the eigenvectors. Eigenvectors. What is the eigenvector? This is Vx, and what is the eigenvalues? Eigenvalue in this case. So in general term, we write a into Vx is equal to lambda into Vx, where this we call eigenvalues and this we call eigenvectors. Okay. So standard form. So that means this eigenvalues and eigenvector, these formulations are coming, we can derive from this vector field, invariant vector field, right. So whatever we learn the invariant vector field, we can use that basic concept to come to the equation which we generally write. That means, the whatever we write from the standard book, we should keep in mind that these expressions are coming from the geometric perspective, right. So, this is the concept of eigenvalues and eigenvectors, the concept this is that we are familiar with. Okay. Next, how to find eigenvalues and eigenvector? Again, you can simply write lambda I equal to, we can write lambda I minus a. If I take the determinant, I will get it, and this one, right. So, I can find these eigenvalues, and again if you write down this equation, you can find out. So, that means, we started with the basis vector for this A matrix, and it turns out to be those basis vectors are nothing but the eigenvectors. Similarly, if we take system 2 that we consider, and if we find out the eigenvalue, that means let us say first A decouple matrix, we write A decouple to represent this and A couple to represent this. So, what is the eigenvalue of A decouple? AI minus A decouple. Let us try to find out. First, write the matrix. It is nothing but lambda plus 2, 0, 0, lambda plus 3, and if I take lambda I minus AD to be 0, it turns out to be lambda plus 2 into lambda plus 3 is equal to 0. So, this will give you minus 2 minus 3. So, these are the eigenvalues, 2 eigenvalues. Similarly, if we consider, that means this is the 2 eigenvalues, and for each eigenvalue minus 2 you will get this one, for minus 3 you will get this one, that you can find out. Now, if we find out the eigenvalues of this, so let us say we can come here. So, A couple, that means lambda I minus A couple. This is nothing but lambda plus 1, because A couple is this, then 1 minus 2 lambda plus 4, and what we will write? Lambda plus 1 into lambda plus 4 plus 2. So, it will be lambda square plus 5 lambda plus 6, which is nothing but lambda plus 2 into lambda plus 3. So, it is the same form, it will be the same. So, that means the transformation does not change, because what we got? We got z equal to m times x, that we got. So, this transformation does not change the eigenvalue, but if we find out the eigenvectors, that means again if we find out the eigenvectors, if we rub up, because I have shown the method how to find, then you will get that these eigenvectors are nothing but 1 1 and 1 2. So, that is we started with that basis vector for the second case, and these 2 basis vectors satisfied our invariant property, right. That means, this Vx2, Vy2 are the eigenvector, and if we form this is simply our A matrix, which transform a diagonal system into a couple system or decoupled system to couple system. Similarly, if I want to convert one couple dynamics to decouple, I need to consider M inverse transformation. That means, if this is my x, this is my z, so my z equal to M inverse x, and here M will be the eigenvalues of eigenvectors of AC matrix 1 1 1 2. So, this couple matrix eigenvectors will constitute the M matrix, and that is the transformation matrix. So, that means comparative study of 2, we can find out the eigenvector, they are the invariant property, and we know about the characteristic equation, and they look like this. So, that means the transformation does not change the eigenvalue, that means their stability property will not be affected, but the nature of the phase portrait will get affected, because we have discussed that as if this, if we see vertically and if we see this from an angle, so it is like an image transformation, right. Either we rotate the page itself, move the page like with an angle by keeping our eye in the same position. Suppose initially the page was just in front of us, right. Now, we make an angle to the page and then it will look like the system 2. That means, this like a inclination comparative motion between I angle and the normal vector of the plane, if we change, then we will come up with this kind of structure. Okay. So, this linear transformation is very much used in image processing. Okay. So, comparative study we have discussed these two, we got the vector field and these are linear transformation. So, it is like image processing. Now, we have discussed about real and distinct cases. The two real cases we saw, if in this case they are negative, because lambda 1 lambda 2 positive means minus lambda negative, then we know that the vector field, if we take initial condition, depending upon, we know how to draw vector field. If we take here, it will come like this. That means, any point you take, depending upon the vector field, you can draw the trajectory for each initial condition, right. So, since this basis vector for these cases are v1, v2 along the x1, x2 axis. So, we know all this because orthogonal decoupled system. So, this is called stable node. Now, if lambda 1 lambda 2 greater than 0 and this, that means the eigenvalues are positive, then you will get it is going away, it will go like away from this, right. It may not be along the line. So, because it is orthogonal basis vector, but it will go away from the origin. So, the bottom line is this: any initial condition if you take somewhat away from origin, it will go out, and the trajectory shape will depends on the vector field. Again, it depends on lambda 1 lambda 2 nature, right, and we know about, in the previous lecture we have discussed how to draw vector field. So, this is our unstable node. The other one can be stable, other can be unstable. That means, the v1 axis is unstable here, you see, because lambda 1 greater than 0, but lambda 2 less than 0 is stable. So, if you take any initial condition here, it will move along this line because this is the eigenvector property and it is a stable eigenvector. If you take any initial condition here, but suppose if you take here, it will try to move towards origin, but then it will be influenced by the other eigenvector, it will go away, and this system is called saddle point. Okay, this is an unstable case. But what we have not discussed is the complex conjugate eigenvalues. So, any matrix which has complex conjugate eigenvalues can be represented by means of a transformation, because we know that transformation, a coupled system can be converted into a decoupled system. We have taken this example, and what is that requirement? We know M inverse, where M consists of, where M is the eigenvectors of this coupled system. So, you can convert it, right. That means, if this is my Z, this is my X. So, Z equal to M inverse X, where M consists of the eigenvectors of the coupled system. Similarly, by the same transformation, if we have a complex conjugate system, we can transform to represent into a regular form. So, this is something called regular form. So, it is something like a decoupled form, but since it is a complex conjugate, you will get off diagonal element will not be 0, where it will get omega. And if you find out, it will be r plus minus j omega, right, and corresponding to each eigenvalue, that means eigenvalues are complex conjugate, and you will find the eigenvectors are also complex conjugate. Now, the question is, how can you draw this complex conjugate eigenvector in the phase plane, because you cannot draw, because it is a real plane, right. So, first let us say we found that, and suppose x of t, we know it is nothing but e to the power rt, because you see why it is coming like this. Suppose we know, if we go back to our x of t is what? X of t we know e to the power lambda 1 t alpha 1 Vx plus e to the power lambda 2 t then alpha 2 t Vy. And since for lambda 1 and lambda 2 both have the same real quantity, that means you will get r plus j omega t alpha 1 Vx plus e to the power r minus j omega into t alpha 2 Vy. So, I can take e to the power RT common for both cases, and that is exactly what I did, and the rest of the term I write as a V. Then what I did, yeah, it is e to the power j omega t I have written, right. Now, we know e to the power j omega t will substitute is equal to cos omega t plus j into sin omega t. And then after simplification, this whole Vm term will appear like this, is a combination, right. And this one alpha 1 Vx, because even if you take this equation, the original equation, if we take t equal to 0, so this will be x of 0 will be nothing but alpha Vx plus alpha 2 Vy. So, this original equation remains and it is x0. Next, that means we got this form. Now, this represents something like, if we look at this, this represents something like, this is our initial condition, this is our real part e to the power RT. So, this is a rotation matrix. That means, if R equal to 0, that means it is a purely imaginary complex conjugate, then you will get e to the power 0 is 1, so complex conjugate, right. So, this is something like if you multiply with this quantity, you can move, that means if you take, that means first let us take, we have x1, x2, x's, where in this plane we have considered one initial vector which is x0. Now, so this is a representation of a system X, and suppose with this representation, now with this initial condition, if we multiply x0 into this rotational matrix, so here this rotational matrix M is like this, MR, rotational matrix. Then what will happen? You will find this rotational matrix will keep on rotating with the same radius, whether it is clockwise or anti-clockwise, that we will see, but it will rotate. And what will be the speed of rotation? The omega is the angular frequency. At this frequency it will rotate, and the good example is alpha beta to dq transformation, where we multiply with a rotational matrix to convert a stationary vector to a rotating vector. Okay. So, that means complex conjugate case, if we take r equal to 0, now we want to see which direction it rotates. For example, at t equal to very small value, so at t equal to 0, we know that omega 0 all these component, but suppose if we are taking a very small, here radius is 0, t, that means we start with time t equal to 0, and suppose we want to find out where will be the location of, that means let us draw, this is our starting point, right. Suppose the starting point where it is t equal to 0. Now, we want to find what happened at t equal to 0 plus delta t, a small time delta t. So, then we can replace this t equal to delta t, right. So, let us replace t equal to delta t, then it will be cos omega delta t, and since delta t is very small, so this cosine angle will be almost equal to 1 cos of this, and sine of that will be very small, it can be approximated by omega t. Then this matrix at x equal to delta t time, since we have taken this quantity to be 1 because r equal to 0, so this matrix will be this quantity to be nearly equal to 1, this will be also nearly equal to 1, this will be nearly equal to omega delta t, and this will be nearly equal to omega minus delta t, minus omega delta t. And if you combine, because our initial state, let us say we have chosen x0 equal to 1 1, right, then we will get the next point. That means, if you look at the x axis, along the x axis, you see this quantity is positive, this is nothing but omega delta t, and if you take along the y axis, this quantity is nothing but minus omega delta t, negative. That means it indicates that this is rotating in the clockwise direction, And if you change this symbol, that means if you take the second case, that means if you just change the rotation angle, it is a clockwise circular motion that we have discussed. Now, if you change it, that means if you now instead of that, suppose you interchange the sign, you multiply with minus 1. So, now it is minus omega plus omega. Omega is a positive quantity. Then it will move, sorry, it should not be like this, it should be here. This is my x1 because it will move in the anti-clockwise direction. So, the clockwise, sorry, it was correct because this drawing was related to the first case. So, this drawing was related to the case when clockwise motion, clockwise. I have not drawn. So, this is related to clockwise motion for this particular system. And anti-clockwise, how does it look like? That means, if you draw it a circle like this, if this is my axis x1, x2, and if I start with an initial condition here, then it will go along this path. So, this is for this particular case. Okay. Now, if we consider a radius which has a negative quantity, because earlier we have not considered radius, we have put radius equal to 0. Now, suppose we consider a radius, here our axis is r omega minus omega r, where r we are taking less than 0. Then the radius will slowly decrease, and that is exactly is happening, it will slowly decrease. Okay? And if we take positive, then it will increase. Let us say minus 1000, then plus 1000, then we are using 0. And let us see how does it look like. So, I think the value we have to increase, the speed of oscillation is not sufficient. So, we need to increase 10 times the given time. Now, you see, if you look at the waveform, it is an oscillatory, right, sustained oscillation. Okay, start with initial condition, and if you look at this particular, so this will be a circle, and this can be represented. And you see the vector field direction, it is the anti-clockwise direction, because we have considered, if we consider the A matrix, if we write the A matrix here, it is minus 1 here and 0 here. So, if we interchange, that means we write 0 here and minus 1 here. Then if we interchange, we want to draw the vector field again, and now you write A, it is, we have interchange, and we can see the vector field. If we draw the vector field, so they are in the clockwise direction. That means it is consistent with our understanding that if this quantity negative, this is positive, then it is clockwise, and if this is positive, this is negative, it is anti-clockwise. That means in this case we are talking about this quantity positive, this negative. So, it is like a clockwise motion that we have seen, it is a clockwise motion. So, this is a vector field, right. Now, so we understood how to draw vector field. Now, we are introducing minus 100 term. That means we are now including r, which is r equal to minus 100, and we are running, and let us see what happened. You see, it is slowly decreasing in the clockwise direction. It is slowly decreasing in the clockwise direction, and it will be clear even the time domain waveform, it is very slowly decreasing amplitude. And if we run again with even higher value, because the rate of decay should be faster, then you will see that it is decaying faster, right. So, it is the speed of that amplitude is decaying faster. So, you can imagine that there is an exponential decay in the amplitude, right, and this will be clear, it is a stable focus. Okay, so, it is decaying. So, our concept whatever we learned is perfect. So, there is no doubt. Now, we can think of this spiral in, spiral out, and if the R is positive, then it will go out, right. Now, we are considering a boost converter. So, the boost converter, we know the ideal circuit, we are already familiar with the boost converter, we discussed multiple times. If we take the state vector to be inductor current and output voltage, then we can write the state space model for q equal to 1 when the switch is on and q equal to 0 when the switch is off. Then we can write down the subinterval 1 and subinterval 2 different A matrix. B matrix will be common, C matrix will be common because it is an ideal converter. Then we can write the state space model which will have for q equal to 1 and q equal to 0, we will get different eigenvalues, right, and eigenvectors. So, then we can model for different configuration, we can get the solution x1 dot from here V in by 2 for the ideal boost converter during mode 1. The inductor current will continuously rise because this equation says it will saturate the inductor and the output voltage will completely fall. So, we have to be very careful about the subinterval 1. Similarly, subinterval 2 we will have this equation. Now, if we want to find the eigenvalues in any mode, particularly we are talking about a subinterval 2, then we will find that lambda, we know how to find out, like this is, if this is my A matrix, then we know the lambda I minus A. If we take the determinant, then we can find out the eigenvalues. And if we do that, then we will find this equation lambda square into lambda into 1 by RC plus 1 by LC equal to 0. Then we can formulate this equation and we will find out the eigenvalue which will look like this, and it will be complex conjugate if the resistive impedance is greater than 0.5 times of the characteristic impedance ZC, which ZC is here. So, since we have already discussed in MATLAB demonstration that how does the complex conjugate eigenvalue look like. So, from there we can actually draw the vector field for a boost converter both on and off state and their combination, and that we are going to discuss, that draw the phase plane. If we discuss the phase plane, that means now if we draw, because we can now draw analytically, suppose if we draw, this is my, let us say, output voltage and the inductor current. Suppose this is my operating voltage Vref, we want to achieve this Vref, and suppose this is my inductor average current where it will operate. So, it will look like this and this. That means, or if I draw using different color, so this is the color when the switch is on and this will be the color when the switch is off, because during switching on the voltage will fall, because you see in this circuit the current will continue to increase and voltage will decrease, right. So, current will increase, that means this direction current will increase and this direction voltage will decrease. But during off time current will decrease, that means it is like this, current will decrease and voltage will increase as long as your capacitor current is positive, right, because if you continue for long time then voltage will again start falling. So, this is the characteristic of the off phase. So, that means we can draw the phase plane, because we need to combine the complex conjugate behavior with real behavior to get our desired behavior. And in the subsequent lecture we want to see, we learn about the vector field, we learn about the eigenvectors. So, we want to reach certain desired trajectory, that means if we take the boost converter, for example, we were here when before there is a load transient. Now, suppose after load transient we want to reach here, so it will go, we want to reach something like this kind of behavior. So, how to do that? This is something like a time optimal behavior. Can you extract? So, for that we need to understand how the trajectory moved during the on time and what should be the our axis where we will turn off the switch, and after turning off how does the vector field look like. So, all these things we are going to discuss. In fact, for boost converter it will be kind of a straight line and then go. It will be something like the straight line, because this is the on time dynamics. So, it is like straight line because voltage current will increase and voltage will fall. Okay. So, this is my current direction, sorry, this is my voltage and this is my current. So, we want to reshape the transient response by using our vector concept and applying the suitable control logic from the geometric point of view. So, with this I want to summarize the recap of vector field of LTI system. We have discussed concept of eigenvalues and eigenvector and their geometric interpretation. Then we also discuss how does it look like for a switch mode power converter, and we did some MATLAB demonstration for vector field for the linear system. So, we will take more detailed vector field for this switch converter with MATLAB simulation in the subsequent lecture. So, I want to finish it here. Thank you very much.